So, hello students, how are you all? I hope you all are in very high spirits. So, in the previous episode, we have completed the theoretical portion of Gauss theorem. We have derived some very important expressions. So, in this particular section, let's try to recap all those important formulas, right? So, these are the particular columns. We'll be writing the expression for the electric field for different cases along with its graphical study. Electric field due to a point charge. We are aware of the formula. Due to a point charge, suppose this is a point charge over here and this is point P at a distance r. Then the formula for the electric field is K, that is 1 over 4 pi epsilon Q divided by r square, right? And graph showing the variation of electric field with the distance. You can easily observe electric field obey inverse square law. E is inversely proportional to the square of the distance of the observation point from the charge. So its graph would be like this. Suppose this represents electric field and the horizontal axis represents distance. So it will be like this. It will meet at infinity. So this is the graph for electric field due to a point charge, its variation with distance r, right? Second, we have discussed the applications of Gauss theorem, and one of the applications was to determine the electric field due to a line charge distribution. So for line charge distribution, you must remember, this was the case. This is a line charge distribution, and here we have considered a cylindrical Gaussian surface, isn't it? We have considered a cylindrical Gaussian surface, and by applying Gauss theorem, we got the expression for the electric field due to this line charge distribution. So for line charge distribution, the formula is lambda over 2 pi epsilon into small r. Lambda over here is obviously the charge per unit length, charge q uniformly distributed over length L, and r is the radius of the right circular cylindrical Gaussian surface, or it's the distance of the observation point from this line charge. So here in this case you can well observe that E is proportional to 1 by r. So in this case the graph would be like this. Suppose this vertical axis represents electric field while small r it represents the distance. So its variation would be like this. Right? Okay. Third, due to a plane sheet of charge. Plane sheet. Now here we have discussed many cases and there are sub cases as well. For infinitely thin sheet, that is when the sheet is considered to be of negligible thickness, then the expression for the electric field at any point is obtained to be sigma over 2 epsilon. Here sigma is charge per unit area, right? I repeat, for infinitely thin plane sheet of charge where the thickness of the sheet is considered to be negligible, the electric field is found to be independent of the distance of the observation point from the sheet of charge. So the expression was obtained to be sigma by 2 epsilon. Since it is constant, independent of distance, so the graph would be like this. This is electric field, this is suppose distance, so it is independent of r. So it will be a straight line parallel to the horizontal axis which represents the distance smaller, right? This is the graph. Now, plane sheet having some finite thickness. Plane sheet having some finite thickness. In this case, you remember the expression for the electric field would be sigma by epsilon. Again, sigma is the surface charge density which is charge per unit area, right? So, in this case, again since it is independent of the distance, the graph would be same. This is a two-dimensional case. Then you remember we have considered two parallel sheets two parallel infinitely thin sheets having equal and opposite surface charge densities, right? That is, this was the case. These are the two parallel sheets, one having surface charge density of plus sigma, the other having surface charge density of minus sigma. This is positive charge and this one supposes negative charge. So here what we have discussed was, in the extreme region the electric field was found to be zero, while in the central region, that is the space between the two plates, the electric field is found to be sigma by epsilon naught. Sigma is the surface charge density. So this was also a very important result which we have discussed, right? We will be making use of these results in the next chapter as well. Fourth, again let's consider two-dimensional case only. Due to a spherical shell. Spherical shell means a hollow sphere where the charge is uniformly distributed over the surface of a hollow sphere. So since charge is distributed uniformly over the area, therefore it must be a two-dimensional case, right? So here there were three sub-cases. If you remember, first is when the observation point lies outside the uniformly charged spherical shell. Capital R was considered to be the radius of the spherical shell. Smaller, as in the above cases also, we have considered smaller to be the distance of the observation point from the charge distribution. In this case, from the center of the spherical shell, right? In this case, the electric field obtained was at a point outside. It was obtained to be sigma capital R square divided by epsilon small r square. So outside, it inversely varies as the square of the distance, right? Second subcase was when the observation point lies on the surface of the uniformly charged spherical shell, on the surface. So in this case, simply we need to substitute the value of small r as capital R. So they will get cancelled and we will be left with sigma by epsilon. This is the constant maximum value. And in the third case, where r is smaller than capital R, that is, we are considering the observation point to be lying inside the uniformly charged spherical shell. There we have determined the value of electric field to be 0. So, in the case of a uniformly charged spherical shell, the net electric field inside it is always 0. Actually, this is a very important concept. It forms the principle of electrostatic shielding. I repeat, electrostatic shielding. Shield means to protect. Some sort of protection against the external electric field. So what happens is, I'll give you an illustration. During thunderstorm or during lightning, if you are driving a car or if you are sitting in a car, then it is always advisable for the driver or the passenger in the car to remain seated inside the car. Because what happens is, the car, which acts as a hollow conductor, it shields the person sitting inside the car from the influence of external electric field, that is due to the thunderstorm or lightning. So the person inside the car will remain safe. So that's the concept of electrostatic shielding. So how do you define electrostatic shielding? It is the phenomena of protection of a body from the influence of external electric field by keeping it inside a conductor, right? So it is basically based on this only. The net electric field inside a conductor is always 0. So that's electrostatic shielding. So if you plot a graph showing variation between E and smaller, then the graph would be like this. Look, this is electric field. This represents smaller. Suppose smaller is equal to capital R and this is center. So inside the electric field is 0, right? From the center till the surface, the electric field is 0. At the surface, on the surface, the electric field is maximum. Over here, the electric field is maximum. And its value is sigma by epsilon. This is what we have discussed, right? And hereafter outside, it obeys inverse square law. Inverse square law means it should be like this. It should meet at infinity. So E is inversely proportional to R square. So this is the graph which properly depicts these three sub cases in the case of uniformly charged spherical shell, right? Now one case is left, uniformly charged solid sphere. That's a three-dimensional case. So fifth one is electric field due to a uniformly charged solid sphere. Please don't get confused between these two articles. This is shell, this is sphere. It's a 2D case, it's a 3D case. In 2D, we make use of the symbol sigma, surface charge density. In 3D, where the charge is uniformly distributed throughout the volume of the body, we'll make use of the term rho, which will denote volume charge density, right? In this case, again, there are three sub-cases. When the observation point lies outside the uniformly charged solid sphere, then electric field outside is given by rho r cube divided by 3 epsilon small r square. Right? This is the expression which we have obtained. You can see outside again this is constant, so it is inversely proportional to square of the distance of the observation point from the center of the uniformly charged solid sphere. When the observation point lies on the surface, so in that case, you simply need to substitute the value smaller as capital R. So what you get is rho capital R divided by 3 epsilon. This is constant maximum value. So again, as was in the previous case, here also the electric field due to a uniformly charged solid sphere at any point on the surface would be maximum, right? Third, when the observation point lies inside the uniformly charged sphere, right? When it lies inside the uniformly charged sphere, then the formula obtained was rho smaller divided by 3 epsilon. You can see over here, rho over 3 epsilon is constant, right? So E inside is directly proportional to distance R. So we'll make use of these three subcases so as to plot graph showing variation between E and smaller. So these were the results which we have obtained, right? Now graphical depiction of this, it will be like this. Look, this represents the electric field. This represents the distance of the observation point from the center of the uniformly charged sphere. Suppose this is the surface. So smaller would be equal to capital R. On the surface, the electric field is maximum. This is maximum value of electric field. So it would be, this is the maximum value, rho capital R divided by 3 epsilon. Right? This is the maximum value. This is the center. Look, inside the solid charged sphere, electric field varies directly as R. So they are linearly dependent. Whenever the two physical quantities are linearly dependent, then the graph between them would be a straight line, equally inclined. It would be in the form of y equals to mx. So it will represent a straight line like this. So inside, electric field varies directly with R. On the surface, it is having maximum value, that is rho capital R over 3 epsilon. And if the observation point lies outside, then it obeys inverse square law. So the graph would be like this. It will obey inverse square law. So these are some very, very important results. Do recap all these formulas, and it's a certainty that in the board examinations, out of these 4 or 5 articles, one article is definitely asked. It can be either of 3 marks category or 5 marks category. So students, please do these articles and try to remember the results as well, along with the graphical study, right?